Okay, you ready? There are times when we are graphing polynomials that we need an exact graph of the polynomial, right? Like in this case, if I graph this right here, what does it tell me? All the zeros, right? What are the zeros? -2, -1, and 5, right? And that's like how we did last time. We got all the factors of the last number divided by the factors of the first number. Those were our possibilities. And then when we graph it, we can actually see where it crosses, right? But there are certain things about graphing polynomials that I don't need an exact graph for, and I don't want to take the time to plug it into my calculator, because I can actually tell some stuff about the graph just by looking at the equation. Those are the things that I need you to be ready for today. You ready? Okay, I need to be able to tell this. I need to be able to tell this. I need to be able to tell this. And I need to be able to tell this. Okay? Now, before I'm going to ask you to tell me what all these things are, I need to make sure you know what they actually mean. Wouldn't that be kind of important? Okay? Well, LC, we could write what it stands for. The words are just longer, so I've been letting people abbreviate that. The leading coefficient. Okay? In this problem right here, what is the leading coefficient? Okay, what does the word coefficient mean? The number in front, right? The number in front. And by definition, leading should mean the first one, right? Now, I had to caution you, what has to be true about this polynomial for it to be the one that's actually in front? What has to be true about the exponents? Don't they have to be in decreasing order? Does that make sense? Okay. For the leading coefficient to actually be the one in the front, this has to be in standard form, which means I start with the highest exponent, then the next highest, then the next highest, and then all the way down until I get to the constant, right? But in this case, that's the way it's listed. So what's the leading coefficient of this problem? 1. Okay? Now, I'm very glad you know that it's 1, but I don't care that it's 1. What I care about is the sign of the leading coefficient. It's positive. That's what I care about. Okay? The sign of the leading coefficient is going to tell me the end behavior to the right. Okay? We'll come back to that in just a second. The degree. Do you know what a degree is? Do you remember what I told you it was last week? Close. I just want you to be a little bit more specific than that. The biggest exponent. Now, did you hear what she said first? The first exponent. Well, if it's in standard form, it is the first exponent, isn't it? But what if it's not in standard form? You have to make sure you're looking for the highest exponent, right? So what's the degree in this problem? 3. Now I need to know the number of turns in this graph. What do I mean by turns? When it changes direction, right? So the best part about this is the number of turns is the degree minus 1. Most people can subtract 1. So what's the degree? 3. So how many turns are there? Excellent. You did a great job subtracting 1. Now, the end behavior looks messy, looks tricky. You're not going to let it be messy or tricky. First of all, because you've seen it before. I've shown it to you before. Okay? Here's how it's going to start. As x goes to negative infinity, f of x goes to, and then also as x goes to positive infinity, f of x goes to. Now we need to fill in the thing that goes right here. Okay, but we're going to always start our in behavior just exactly like that. Now before, you could do it now, but I think it would be helpful if before we figured out the in behavior, we actually do the graph. Okay, now what did I say about the leading coefficient? It's positive and it tells us the right behavior. Okay, so if it's positive, which direction is it going to the right? It's going up. What if it was negative? Which direction would it go?
Down.
Down. Okay. Now, how many turns does it have? 1, 2. Do you see how it changes directions 2 times? That's what I mean by turns. Okay. Now, does this look exactly like the graph I showed you a second ago?
Yes.
Should I show you again to make sure?
Oh, no.
Does it look exactly like that?
No.
Do I care that it's exact, though? No, we already said that, right? We want a general graph, and what I care about in this graph is the end behavior, right? The number of turns and the end behavior. Does this graph have 2 turns? Right? One's here, one's way down here where we can't see it. And does the right go up and the left go down? Yes. Do you see how they are the same then? Yes, they are not exact, but they look the same. Okay? Now let's go to our end behavior. As x is going to the left, where's y going?
Down.
So where's it going?
Negative.
Negative infinity. And as x is going to the right, where's y going? Up. So what? Infinity. Done. Now, can I use my calculator to do all of this work? Yes, but wouldn't it take longer to press it in the calculator just to do all the work? Yeah. This takes a lot less time than it does to press it in the calculator, right? Can I use my calculator to check and make sure? Oh, yes. Right? Does that make sense? Okay, should we do another one? Yes, okay. Y equals 4 minus x to the 4th plus 2x squared minus 4x to the 3rd plus x. So we just cry and stop? Is that what happens?
Yes.
No? Okay. You're going to be asked for the leading coefficient. You're going to be asked for the degree. You're going to be asked for the, oh geez Louise, T-U-R-N-S, asked for the number of turns, and you're going to be asked for the end behavior. Now for the end behavior, I'm going to go ahead and write as x goes to negative infinity, f of x goes to, and as x goes to positive infinity, f of x goes to. I'm going to go ahead and write all that. I'm sorry? Yes, that's how we'll always start the end behavior. Okay? Now, again, we still have 2 things to fill in right here, but that's how we're going to start the end behavior every time. That's a great question. Now, does anybody see a problem with this problem?
I do.
What's the problem? Not your problem. I already know that. Just what you got? So, like, what's the problem with this problem?
It's not standard.
It's not standard, right? It's not in order. So what do we have to look for? The biggest one, right? So I'm going to go ahead and circle that whole thing. Okay? Why am I circling that whole thing?
That's the first.
Right. Okay? So what is my leading coefficient? -1. Because I circled that whole thing, I'm also seeing my leading coefficient, right? Now, is it okay if I put -1 as my leading coefficient? Yes, but what I really care about? The sign, right? So I can go ahead and draw my right behavior already, can't I? The leading coefficient tells us our right behavior, not the left behavior, but the right behavior. Okay? What's the degree of this problem? 4 How many terms are there then?
3.
3, because that's the degree minus 1. 1, 2, 3 turns. Now that I have it drawn, can't I see my end behavior? As I'm going to the left, where's the graph going? Down, so negative infinity. As the graph is going to the right, where's the graph going? Down, so done. Questions?
Wait, so the 4 doesn't matter at all?
What for?
The 4 in front.
No, not at all. This doesn't matter at all. It would only matter if what? If this was in order, right? And if it was in order, it wouldn't be in front, would it? That would be in front. That 4 would actually be out the way at the very end, wouldn't it? And then these two terms would be switched, right? Am I asking you to put it in order before we start? No. Can you if you want to?
Sure.
Yes. Right? But I'm saying find the greatest exponent, circle that whole term, because that's going to tell you everything you need to know for this. And it's going to tell you your right behavior so you can find your left behavior based on the number of turns. Any questions? Do you need another example? You're feeling pretty confident about this? Good job.